Welcome again to another video on waves. This time we'll cover refraction, what you need to know and what you need to do with that knowledge. Outcomes today: you need to be able to state what's meant by refraction, you need to be able to identify the normal, the angle of incidence and the angle of refraction. You need to describe what happens to the wavelength, speed and frequency of a wave as it refracts. So let's just get this out of the way. What is refraction? Refraction is when a wave changes speed as it moves from one material to another. All waves refract, but it's most obvious with light. The more dense the material, the more it refracts, and it usually causes a change in direction of the light, but not always. You'll have seen the refraction of light before. It's an optical effect that you'll have experienced without knowing that refraction is the cause. Here you see the pencil appears broken in the glass of water. You'll have seen the same effect with a drinking straw. We all know it's not broken, it's an optical effect. It's caused when the light moves through the water and then into the air. The cat is not obese, it's a weird optical effect caused by the refraction of light. In both of these cases, the light we see coming from the pencil and the cat have refracted and changed direction as they move from the water to the air. This change in direction has caused the object to appear distorted. We get the same effect when we use a magnifying glass or while wearing glasses. So what's happening to the light? An incoming ray of light will strike the surface of a rectangular glass block. In physics, we're usually interested in the angles that are made by the light, so we draw an imaginary line called the normal. The normal is used to measure angles from. All angles are measured from the normal, never ever from the surface of the glass. The normal is always drawn at the point where the light meets the glass and is drawn at 90 degrees, or right angles to the surface of the glass. We can now use our normal line to measure the angle of the incoming light. This is called the angle of incidence and is usually labelled with a small I. It's important to note that the speed of the light in air is 3 times 10 to the power of 8 meters per second. When the light enters the glass it refracts, in other words it changes speed. The speed's slower in the glass, it's only 2 times 10 to the power of 8 meters per second. This causes the light to change direction. I'll show you why this happens shortly. Let's use our normal to measure the new angle. It's called the angle of refraction. It's usually represented with the symbol small r. We find that not only is the speed in the glass smaller, but the angle in the glass is smaller too. The beam of light continues and strikes the new glass-to-air boundary. Let's draw a new normal to allow us to see what's happening with the angles here. The angle the light makes with the glass surface is now the angle of incidence, because it's the light incoming to the glass surface. The angle here is identical in size to the angle of refraction we measured earlier. This isn't always the case, but the two glass surfaces the light has passed through are parallel, so that will be the case here. When the light exits the glass into the air, it speeds up again, just as the angle got smaller as the speed got smaller. Now the angle must increase as the speed increases again. This is our new angle of refraction. In fact, the angle will be the same as the original angle of incidence. It's now travelling at the same speed as before, so the angle will be the same too. Please remember that everything's smaller in the glass, the speed and the angle. So why does the light change direction? You don't need to know this for a Nat 5 exam, but I'm sure some people will be curious. Waves obey the Huygens principle. Look that up on Wikipedia or something if you want more details, but I'll try and simplify it here. The Huygens principle was proposed by a Dutch physicist called Christian Huygens in the 1600s. He's a bit of a hero amongst physics geeks, so he's had space probes and stuff named after him. The Huygens principle states that each point on a wavefront is itself a source of waves. Now, that might sound a bit complex or boring or both to you, but it's used to explain a lot of wave phenomena, such as diffraction and refraction. In a nutshell, it means that the wave just can't break apart when it meets a boundary. One part of the wave is always kinda hanging on to the rest of the wave. In the animation we see a series of wavefronts crossing from one boundary to another at an angle. The waves in the second material slow down, but because the slower part of the wave is hanging on to the faster part, the Huygens principle, it causes a change in direction. You would see the same thing if a car was travelling along a road and one side of the car came off the road and ran along a muddy field. The side in the muddy field slows down and the bit of the car on the road continues at the same speed. This would cause the car to swerve towards the slower side, the muddy field side. Drivers will know about this when one side of the car goes through a puddle while you're going quite fast on a motorway or something. The car will pull towards the puddle, which is a sphincter tightening experience. The same thing's happening with the waves here. Pay closer attention here though, and we can see some other interesting things about the wave. Notice that not only does the speed decrease, the wavelength in the second material is smaller too. However, if we count the number of waves entering and leaving the second material at any given time, we see the same number of waves entering and leaving. Another way of saying this is that the frequency remains unchanged. So when refraction occurs, the speed and the wavelength always change, but the frequency never changes. In the glass, the speed, the wavelength, and usually the angle are always smaller than in the air. If you're ever curious about whether light will speed up or slow down as it moves from one material to another, please remember that you've got this table at the beginning of every assessment and it's got the speed of light in materials and that'll tell you. I mentioned earlier that the direction doesn't always change because there's one situation where it remains the same. It's when the light strikes the glass at 90 degrees or directly along the normal. We could say that the angle of incidence is 0 degrees, but the light still refracts. The speed decreases, so does the wavelength, but we'd see no change in direction here. Sometimes you'll be asked questions about light in a semicircular glass block. The same principles apply here. As long as the light is aimed at the centre point of the straight edge of the glass, then it will strike the curved surface of the glass at right angles. It's just a property of circular things. The light is travelling along the radius of the circle. Anyway, we're more interested in what's happening at the flat surface of the glass to air boundary. We'd draw a normal, as normal. Get it? The light coming through the glass forms the angle of incidence. As it leaves the glass, it refracts. It speeds up, so the angle and the wavelength would both increase. Frequency must remain the same. Next time you're at the swimming pool, go to the deep end of the pool. Unless you can't swim, stick to the kids' pool, wear armbands. But from the deep end of the pool, the floor of the pool always appears shallower than it actually is. In fact, anything in the water will appear at a shallower depth than it really is. Why? Let's see what's happening with the refracted light. So light will reflect off the fish in all directions, but some of it will reflect in this direction. Let's draw a normal to measure some angles. A 90-degree line where the light meets the new surface. When it crosses the water into the air boundary, it refracts. This light will speed up, its wavelength will increase, and its angle will increase too. This light will reach the eye of the observer on the side. But what will the observer see? Well, the observer will see the fish's position at this new point because their brain tells them that's where the light has come from, so it must be the position of the fish. It appears shallower than it actually is. Now let's have a look at some exam questions on refraction. So we've got a student on a pier and a fish in the water, just like the example we just did. You're asked to complete the diagram to show the path of a ray of light from the fish to the student. You should include the normal in your diagram. If you want, try and remember how this ray diagram looked. Try and roughly sketch it out as you would in an exam. Pause the video and give it a go if you can. So just like the previous example, We've got some of the light reflecting from the fish to the surface. We put a normal in at the boundary between the air and the water at 90 degrees to the surface. And then we show the refracted light going towards the student. Because the speed in the air is bigger than the speed in the water, the angle will be bigger in the air as well. For the second example, we've got a semicircular glass block here. We're given two angles, 67 and 50 degrees. A ray of monochromatic light passes through a glass block as shown. Which row in the table is correct? Pause the video, try to come up with an answer. Now you've got to be really careful here, because if you're given a question like this in an exam paper, 9 times out of 10 the SQA are going to try and screw with you a little bit. A lot of pupils will just say the 67 degrees and the 50 degrees, and they'll pick answer E. But always remember, the angles of incidence and the angles of refraction need to be measured from the normal, and these are not measured from the normal, these are measured from the surface of the glass. That's not the angles of incidence and refraction. So the angle of incidence has to be 23 degrees because the 67 plus the angle of incidence needs to make up 90, and the angle of refraction needs to make the 50 up to the 90, so it needs another 40 degrees. So we've got 23 degrees and 40. Your answer is A. So we'll briefly go over the outcomes. What is meant by refraction? Refraction is the change of speed when light moves from one material to another, but we could also say it's the change in wavelength as light moves from one material to another. Don't ever be tempted to say it's when light changes direction, because we know that that is not always the case. You need to be able to identify the normal, the angle of incidence and the angle of refraction. So the normal, an imaginary 90-degree line made with the surface at the point where the light meets the surface. We use the normal to measure the angles. The angle of incidence is the angle that the incoming ray makes with the normal, and the angle of refraction is the angle between the refracted ray and the normal. And what happens to the wavelength, speed and frequency of a wave as it refracts? The frequency never changes, but the speed and the wavelength do. If the speed increases, so does the wavelength. If the speed decreases, again, so does the wavelength. I hope you've found this useful. Please like and subscribe, and I'll catch you in the next one. Cheerio!